A2 Maths, vectors in 3 dimensions. So last year in year 1, you started looking at vectors, but you looked at vectors only in a 2D environment. So you always had them on a flat plane, like a flat piece of paper. So they were always only in 2 dimensions. They went across and they went up, very much like your XY grid. That's what as far as you looked at. What we're going to do in year 2 though is look at extending that into 3 dimensions. So just so we make sure we fully understand what it actually means to be in 3 dimensions, you've got this sort of cuboid shape here, and if I want to look at a vector in 3D, instead of just going across and up like that, like you would have in 2D, because you've got 3D, you would have this extra dimension here of how far up to go. And seeing as we live in a 3D world, it does make sense to fully understand how to solve problems in 3-dimension vectors as well. All right, so look at the only difference between that and what you did last year. Last year, don't forget you would have R underlined for your notes. You'd underline that because it's a vector. Last year you would have just A and B, but now we've got this A, B, and this extra dimension C. So let's have a look at what difference it actually makes compared to what you practiced last year. Okay, so the first thing we just want to make sure is that's where the R is understanding what we mean by a unit vector. So the unit vector is any vector that has a magnitude of 1. So you would have done that last year as well. You'd understand what a magnitude is, and you'd understand that a unit vector is any vector that has a magnitude of 1. Now the common ones we looked at were these two. We looked at the I and the j vectors. So the I vector, well last year you didn't have the bottom number, was 1, 0, and the j vector was 0, 1. Now because we've got a third number at the bottom now, we can extend it to another basic unit vector, which would be 0, 0, 1, and that would be the vector k. Notice these are vectors, that's why they're in bold, so you'd underline them, I, j and k. Notice that if I squared each of these numbers and square root it, I would get a value of 1 because they are unit vectors. But also just be aware that these are the only 3 unit vectors. There's an infinite set of unit vectors out there, and we'll look at some of those in a little while. Okay, so that means that if I could write it in unit vectors, this A, B and C, if you remember again, you can rewrite a column vector using components A, B and C. So just in your notebooks, just make sure you're able to flick between a column vector, A, B and C, or you could write it in its component forms like that, A, B and C. Now these two are identical. It does not matter which one you prefer, which one you want to use. Sometimes you might prefer to write it in this form, sometimes you might prefer to write it in this form. It doesn't matter. Okay, they are both equivalent to each other. They're both exactly the same. Okay, right, get down what you need in your notebook. Right, so the magnitude, as we just mentioned there when we talked about a unit vector, the magnitude was the size of the vector. Now what's important in this case is that we can write it now with these modulus signs. You didn't understand what these modulus signs were before, but now you know. These modulus signs make negatives positives, and the way they do that is they square it and they square root it. Now for most numbers, like for example just -2, the modulus of -2 is just 2. And the reason why that's true is because you take -2, you square it, you get 4, and you square root it and you get back to 2 again. But another way of thinking about the modulus is the magnitude of it, the size of it. So -2, if you've travelled from 0 to -2, you've travelled a distance of 2, just in the negative direction. Okay, so it's the magnitude or the scalar part of it, as we often call. Right, how does that work with vectors then? Well, last year you did this. You said that if I've got a vector A, obviously that's just going to be the magnitude A and B, and I could work out the magnitude of the vector AB because I could just use a bit of Pythagoras. I know that's going to be A plus B. What's the magnitude of A plus B? It's going to be A squared plus B squared square rooted. That's what it's going to be. Okay, so once I know that fact just there, I have this length here, this size. Right? So that's how you find the magnitude of any sort of vectors. You just take each of its components, you square root them, and you square root the answer at the end. Now in 3D though, of course, we're looking at this extra component C. So there's my A, there's my B, there's my C. But I've just worked out this length here. Okay, this length is root A squared plus B squared. This one is just going to be C squared. Okay, I know that because it's just its magnitude, just its length. So what I could do, or square root of C squared, I should say. If I want to work out R, I could do that side squared plus that side squared, all square rooted. I also know that it's going to be a right angle, just because the C value comes straight up. It's perpendicular to it. So what I could do is I could use Pythagoras' theorem again, and I could do this. There's one side squared. That's the square root of A squared plus B squared, plus C squared, all square rooted. Now with a little bit of neatening up, I can see that the square root there and that square is going to cancel out. So what I end up with is that answer just there. That the magnitude of R equals the square root of A squared plus B squared plus C squared. So I don't need to work them out individually. What I can do is I can just work out each of the components of the vector, square them and square root. So if I've got a vector like this, A, B and C, I can just square each of those components and square root to the end. Make sure you've got that fact down in your notebook. Another formula I'm just going to give to you as well, we're going to look how to use it in a second, is how to write a unit vector in that direction. Okay, so if that direction there is all the way, what I want to do is I want to look at a single unit of that. And the reason why you do that is similar to the sort of unitary method used at school. So for example, you would have had a problem like this. It cost you £10 for a 7 meters of chain. How much does it cost for 5 meters of chain? And what you do with those types of questions at GCSE is you found out what you get for maybe what 1 meter was worth, and then you times it up to 7 meters. Okay, so that's the sort of problem that you did. Do exactly the same with these sorts of problems. If you can work out what a unit value of that vector is, then you can times it up to get you whatever other one you want. So if I can work out what one lot of it is, I can then times it up to get other multiples. Okay, but then how do I figure out what one lot of that is? Well, the way you do it is by using this formula just here. Okay, you work out, you've got the R value, which is just going to be your A, B and C, and you divide each of those elements by this value, whatever this comes out to be. Okay, so whatever value this comes out to be, its size, you divide it by its length just there. Okay, so just make sure you got down what you need in your notebook. We'll look at an example of how to use that now. Okay, so I'll just give you a chance to write down the question in your notebook and we'll have a look through it. Okay, so a motorbike is travelling at 28 miles per hour, so we know that, and we've got a rough idea of which direction it's travelling in. So what we want to do is we want to work out the position vector in terms of I, J and K. Okay, so what's its position vector? So the reason all you've got at the moment is a direction. You know it's travelling 6 in the I, 2 in the J and 3 in the K, so it's clearly going uphill somewhere. Okay, so we know it's travelling in this direction. We also know it's travelling at 28 miles per hour. But what I want is I want to know what vector it's travelling in so that I can find its magnitude to be 28 and it's going to be some multiple of this. It has to be some multiple of this because then any multiple of this is going to be parallel in the same direction. Okay, so how do I do that though? How do I find a vector that's parallel to this, some multiple of it, that's got a magnitude of 28? And we can do it using that sort of idea of finding a single unit. So in this case, what I'm going to do is I'm going to find the direction the bike is travelling in, and I want to find the unit vector for that. So I can do that using this formula just here. So the R value is this, and what I'm going to do is find the magnitude of it first of all. So I want to work out the magnitude of R. Now I can do that by just squaring each of the elements and square rooting. So once I've done that, that comes out to be 7. That's nice. And then once I've got a 7, I can just write this back into ij's and k's form. So there we go. And now I want you to just check now at this stage. Just pause it for a minute. Get your calculator. Try 6 sevenths squared plus 2 sevenths squared plus 3 sevenths squared square rooted. And hopefully you can convince yourself that what you found there is a unit vector, because the magnitude of it comes out to be 1. Okay. But what's also important about this unit vector just here is it's definitely in the same direction as this one. In fact, if I times it by 7, you can see it's just exactly the same as this. So these two are in the same direction. If you plotted those down and drew them, they would be exactly the same line in exactly the same direction. Okay, they're just parallel with each other. Now then, what I want to do though is I don't want just one lot of it, I want 28 lots of it. So because I know the speed for that is magnitude of 1, that's like 1 miles per hour. What I can do now is I can work out what 28 miles per hour is. So in this case, 28 lots of that vector just there would get me 24i minus 8j plus 12k. Oh look, that is definitely a multiple of this. I can see that, it's 4 lots of it. But also, just as importantly, it has a magnitude of 28. If you try 24 squared plus 8 squared plus 12 squared square rooted, out pops 28. So you've worked out its position vector for that bike. Okay, so pause, get down what you need. Okay, so look at another exam question. So again, I'm just going to stop there, give you a chance to write down the question. You might want to have a go at this one yourself, roughly. There's no problem with that at all. Okay then, so a ship has an initial position, a bearing 125, distance 25 miles. So I'm going to think about that bit first. So if I think about bearings, I know that bearings work like this. There's my north line. I always go clockwise on a bearing. So 125 is going to go past that 90 and down here roughly in this sort of direction. I'm also going to just roughly plot in 25. So just a rough sketch. So I know its initial position is going to be something down here. So I don't want you to get protractors out and rulers out or anything like that. Just a rough sketch. There we go. That'll be fine. The ship's roughly in that position. That gives me an idea, especially when I start looking at it in component form later on. So that's fine. Right, once I know that, I can also play with the angles. I can think about what sort of triangles I'm going to use. So in this case, I can calculate the components I and j. So how far across, how far down. And I could do that using basic trigonometry. So because that's 90 to there, this angle here is going to be 35. So I could use my trigonometry skills, and this is where you definitely could just pause and finish it all off. So I could use my trigonometry skills. I can work out what the A value is, which is going to be 20.5, which makes sense. I can work out what the B value is, and the B value in this case is going to be 14.3. But do not forget that in components, it's going across and then down. This is what is a good idea to do a rough sketch, because you can clearly see that you need to go down to get to S. So 14.3 minus 14.3. The balloon is 2 miles above the ship. So this ship, 2 miles out the screen towards you, is where the balloon's going to be. So how do you write the balloon's position in component form? It's 20.5 in the I, it's 14.3 in the J, and then it comes out the screen an extra 2 miles. So it's position vector of that. Okay, so again, just pause, get down what you need. Okay, so we're going to look at one last thing to do with vectors in 3D, and that's if we want to get the angle between them. Now, the problem with trying to picture the angle between them is we're looking at a 2D flat surface in front of you. The computer screen or the piece of paper in front of you is a flat screen. So if we're trying to picture 3D, it doesn't quite work. But it doesn't stop you being able to just do a rough sketch. So that's what I'm going to do. I'm just going to do a rough sketch. So O to A is going to be 1, 3 minus 2. And O to B is going to be 3 minus 4, 2. And I'm looking for the angle between those two. Okay, so that's the sort of idea of what I'm doing. It doesn't matter whether B's sticking out the screen and A's miles back from the screen. That doesn't really matter. It's just a rough sketch. Okay, what I need to do though is I need to calculate these lengths. Now I can do that because I know how to work out the size of O to A, because I can work out the magnitude of that. So that one there is going to be 1 squared plus 3 squared plus 2 squared, square rooted, root 14. This one, 3 squared, 4 squared, 2 squared, square rooted. Okay, so you can work out both of those values there. Now, if you look at this question here, you can see now you're getting closer to just a normal trig question. I've been able to use a cosine rule, hopefully. But to do the cosine rule, I need to know this length here. Now, I can work out that length there because I know how to work out A to B. I can work out A to B because I can do O to B minus O to A. Okay, so I can work it out like that. It goes from A to O to B. So I can work it out using this technique I've seen before. If I did that, then I'm going to be, don't do root 14 take away root 29 or anything silly like that. So root 29 taken away from root 20. Don't do root 14 taken away from root 29. It's not the square roots you're taking away, it's the vectors. So you're doing that vector there, take away that vector there. And if I do that, I'm going to end up with 2 minus 7, 4. To get from there to there, I would do 2 minus 7 and 4 out the screen. Can I work out the length of that? Yes, I can do 2 squared, 7 squared, 4 squared. So therefore, I get root 69. And once I'm at that stage there, you can now see we've got a cosine rule question, and I can work out the angle theta. So using the cosine rule, there we go, b squared plus c squared minus a squared. I should be able to stop there, and you should be able to finish this off yourself. Okay, so let's see what you did. Did you get this number here? Okay, by substituting those values in. And then once you've got that, you get theta to be about 103.2. So the angle between those two lines would be 130.2. So very well done if you managed to get that. Right, have a go at the review exercise. So it is the review exercise. It's not just an exercise itself. On page 384, please.